All right, let's just jump right into it. Quantum mechanics is full of some seriously strange ideas, right? But there's one that, well, pretty much everyone agrees no one truly understands it, and that's quantum spin. The funny thing is, this one incredibly elusive property is basically responsible for the structure of, well, all matter.
So what even is it? We're going to try and get a little bit closer to understanding this truly bizarre feature of our universe. But first things first, we've got to clear up one huge misconception right out of the gate.
Yeah, despite the name, quantum spin has almost nothing to do with actual physical spinning, like a spinning top or a planet. And the story of how physicists figured this out, well, it all starts with a very peculiar experiment.
So let's go back to 1915. An experiment was done that seemed to break a fundamental law of physics, and it used a surprisingly simple setup.
Okay, so picture this. You've got a cylinder made of pure iron, and it's just hanging there, totally still, suspended by a single thread. It is completely motionless. And then you flip a switch, turning on a magnetic field around it, and all of a sudden the cylinder starts to turn. Now, this is weird. It looks like it's violating the conservation of angular momentum. I mean, there was zero rotation to begin with, so where on earth did this new rotation come from? The most logical explanation at the time was that something was already spinning, just on a microscopic level. The idea was that the electrons themselves were like these microscopic spinning tops, and when the magnetic field was turned on, all these little electron tops lined up, and in the process, they transferred their combined spin, their angular momentum, to the whole cylinder, making it rotate. It's a really neat, tidy explanation, except it's completely wrong. See, as physicists started to look closer at this idea of a physically spinning electron, they ran into some massive reality-breaking problems. The brilliant physicist Wolfgang Pauli was one of the first to really dig into this and point out the flaws. He did the math, and he figured out that for an electron to generate its magnetic field by actually spinning, its surface would have to be moving impossibly fast. But even more fundamentally, our best measurements tell us that electrons are point-like particles. They don't even have a surface to spin in the first place. That's right, we're talking faster than the speed of light. And this isn't just a little bit off, it's a fundamental violation of Einstein's theory of relativity. So with that, the whole classical picture of a spinning little ball of charge just completely falls apart. So, if it's not spinning, what is it doing? The next major clue came from another landmark experiment, one that really pulled back the curtain on the truly quantum nature of this mysterious property. So in the Stren Gerlach experiment, physicists fired a beam of silver atoms through a specially shaped magnetic field. Now each silver atom has a single lone electron in its outer shell, which makes the whole atom act like a tiny magnet. That magnetic field should push them up or down depending on how they're oriented. And this is where reality just completely defied all expectations. Logically, you'd think these little atom magnets would be oriented randomly in all directions, right? So when they pass through the field, they should create a continuous smear on the detector screen. But that is not what they saw, not at all. Instead, there were only two distinct points. The atoms were deflected either all the way up or all the way down. There was absolutely nothing in between. This property wasn't continuous, it was quantized. It could only take on one of two values. Pauli gave it this wonderfully descriptive, if maybe a little clunky name. There was just no classical way to explain this binary up or down nature. It was something brand new. So, what we have is a property that acts a lot like angular momentum, but it isn't rotation, and it can only have two values. To describe something this strange, physicists needed a completely new kind of mathematics. And this is where the spinner comes in. Pauli realized that the existing quantum equations just didn't account for this two-valuedness. He discovered that by describing the electron not with a simple number, but with this more complex object called a spinner, he could finally make it all work. And what spinners describe is a very, very weird kind of rotation. For every object in our daily lives, a 360-degree rotation brings it right back to where it started. Simple. But for a particle described by a spinner, like an electron, that's not true. After one full 360-degree turn, it comes back to the same spot, but its mathematical description, its phase, is now inverted. The best analogy is to think of a coffee mug attached to some ribbons. One full turn twists up the ribbons. To get both the mug and the ribbons back to their original state, you have to turn it another 360 degrees, a full 720 degrees in total. That's the bizarre rotational nature of spin. Okay, so spin is deeply strange, but why should we care?
Because this bizarre property isn't just some quirky footnote in physics. It is the fundamental reason that stable matter, and therefore you and I, can even exist at all. You see, this one property, spin, divides all the particles in the universe into two fundamental families. On one side, you have fermions, like electrons. They have what's called half-integer spin, and they are the building blocks of all matter. On the other side are bosons, like photons, the particles of light. They have integer spin, and they carry forces. And this seemingly small mathematical difference leads to a profound, universe-shaping difference in how they behave. The crucial point is this, that half-integer spin of fermions leads to a simple but incredibly powerful rule called the Pauli exclusion principle. It states that no two fermions can ever be in the exact same quantum state at the same time. You could say they're fundamentally antisocial. And that one rule changes everything. It's why electrons in an atom can't all just collapse down into the lowest energy level. They're forced to stack up into these distinct shells, creating the entire structure of the periodic table of elements. It's the reason atoms have volume, why matter is stable and solid, and it's literally the reason the atoms in your feet push back against the atoms in the floor so you don't fall through it. This obscure, bizarre quantum property is the very foundation of chemistry and the tangible world we experience.
So let's circle all the way back. We started with a simple, rotating iron cylinder and this intuitive idea of a spinning electron. We saw how that idea was physically impossible, and how experiments revealed a bizarre, two-valued quantum property that requires a full 720-degree turn to get back to the start. In the end, what we call spin isn't really rotation in space. It's an intrinsic, fundamental property of a particle, just like its mass or its charge. It hints that particles aren't just simple points, but something much, much deeper. And maybe, as one source so beautifully puts it, they are strange little knots in the very fabric of reality itself. And that just leaves us to wonder, what other fundamental truths are hidden behind names we think we already understand?